Hello everyone, my name is Naina and I'm from the Buddhi Academy. So today we'll continue with the chapter that is structure of atom, and in last video we have seen about the quantum mechanics model, right? So we have seen about quantum mechanics model. So in this class we'll see about the shape of the shells. Now we have seen key in quantum mechanic model, it basically deals with the three quantum numbers, right? What are the three quantum numbers? First is the principal quantum number. Second one is the azimuthal quantum number. One is the magnetic quantum number. Since these three cannot explain certain points, there was one more quantum number that was added, that is the spin quantum number, right? All the quantum mechanics model, they follow their structuring things on the basis of these three quantum numbers. Now let's see the structure of the atom or the shape of the atomic orbitals. Now what are the shape of the atomic orbitals? Now atomic orbitals, they have wave function, that is psi. For an electron in an atom has no physical meaning. Okay. Now it is simply a mathematical function of the coordinate of the electron. This doesn't have any physical meaning in the orbital, but this is there as a mathematical function for the coordinates of electrons. Now different orbitals, the plot of corresponding wave function as a function of r. R is the distance from the nucleus. Now if this is an atom, this is the nucleus, r is the distance from the nucleus. So you can consider it to be a radius. Okay. Now according to German physicist Max, the square of wave function, that is psi square, at a point gives the probability density of the electron at that point. So this psi square, it can give you a probability of how much electrons are present there. The density you can know with use of this psi square. Okay, so the variation of psi square as function r for 1s and 2s orbitals are given here. Okay, so this is with the 1s and 2s, okay, the psi square. Now, it may be noted that for 1s orbitals, the probability density is maximum at the nucleus and it decreases sharply as we move away from it. Now, you can see the density is more in the nucleus part. So, this is the nucleus part, right? So, the density is more here. But as we go away from the nucleus, it decreases. Now, for 2s orbitals, okay, the probability of density decreases. Here you can see there is a decrease, right? So it decreases, then it increases sharply, and again it decreases at the end. So on the other hand, 2s orbitals, the probability density first decreases sharply to 0. You can see, right? Then starts increasing. Then it started increasing here. It started increasing in this area. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. So, after certain distance, it again decreases. Why it decreases? As the distance from the nucleus is increasing. So, this is the nucleus. Okay? From the nucleus, the distance is increasing. So, as the distance of r increases, the value reaches to 0. Okay? The region where this probability density function reduces to 0 is called nodal surface. So this region where it decreases to 0, this entire region is known as nodal surface. Okay, this is known as nodal surface or nodes. Nodal surface or simply nodes. Okay. Now, in general, it has been found that ns orbitals, that is 1s, 2s, 3s, 4s, or the ns orbitals, have n minus 1 nodes. Okay, that is number of nodes increases with increase in the principal quantum number. Okay, that is your n. Now in other words, number of nodes for 2s orbitals is 1, 2 for 3s orbitals, and so on. So as the number of principal quantum number increases, that is 2, 3. So similarly, your nodes will also increase because it is n minus 1, right? So 2 minus 1 is 1. So for 2s it is 1. 3 minus 1 is 2. So for 3s it is 2. So this will go on increasing. These probability density variations can be visualized in terms of charge cloud diagram. Okay, so it can be observed using charge cloud diagram. So this is the charge cloud diagram. Okay, you can see, right? This is known as charge cloud. In this diagram, the density of the dots in a region represents electrons probability density in that region. So here, these dots means that there are electrons present here. Okay, density of that electrons in that region. And next is the boundary surface diagram. So that one is the charge cloud diagram. Now we'll see about the boundary surface diagram. Of constant probability density for different orbitals give a fairly good representation of the shape of the orbitals. In this representation, a boundary surface or contour surface is drawn in space of an orbital which the value of probability density psi square is constant. So here this is what a boundary surface diagram for 1s and 2s orbital is. Now for that boundary surface diagram, it it represents an orbit. Orbitals give a fairly good representation of the shape of the orbitals. It gives a fairly good representation of the shape of the orbital. So this is an orbital. Okay. Now, this representation, a boundary surface or a contour surface is drawn. Boundary surface or contour surface, there is a sharp boundary you can see. Right here, even though it is drawn in a circle, but there is no boundary. See, outside also there are density of electrons shown, right? But here you can see a sharp boundary. Now, in space of an orbital which has a value of size probability density psi square is constant. Here the psi square is constant. Here it is increasing, decreasing, right? But here the psi square is constant. In principle, many such boundary surfaces may be possible. Okay, many such orbitals are possible. However, for a given orbital, only that boundary surface diagram of constant probability density is taken to be good representation of the shape of the orbital which encloses a region or a volume in which the probability of finding an electron is very high, say 90%. So here what happens, the orbital, the boundary of such diagrams, boundary surface diagram of a constant probability density, here it says it's for a density, probability density where it is constant. So for a constant probability density is to be represented of the shape of the orbital which encloses a region or a volume where you can find an electron. You are sure ki 90, you are 90% sure ki you can find an electron in this region. Okay. Now the boundary surface diagram for 1s and 2s orbitals are given here. As I showed you, this is 1s and this is 2s orbitals. Why there is a need to draw a boundary surface diagram? So which bounds a region in which the probability of finding an electron is 100%. It says ki where there is a boundary surface diagram, you are 100% sure ki you can find an electron in there. Okay, so the answer to this question is that the probability density, that is psi square, has always some value, however small it may be. Okay, this psi square, it has a value, even though it can be a smaller value, but it has a value at any finite distance from the nucleus. Within any distance, even if you take it from here to here, within this range also you can get a probability. Okay. So it is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding an electron is 100%. So it is not possible to draw a boundary surface diagram this much, because you can get anywhere, right? This big you draw anywhere you can get. So you can't specifically mention ki this is the size. So boundary surface diagram for s orbitals is actually a sphere centered on the nucleus. Okay, so here you can see there is a sphere centered nucleus, right? So this is the nucleus part, both this thing. In two dimensions, this sphere looks like a circle. So in two dimensions, it looks like a circle, but it is actually a ball type thing. So it encloses a region in which probability of finding an electron is about 90%. So you can find an electron in this sphere and you are 90% sure that you can find it. Now, first, we see that 1s and 2s orbitals are spherical in shape. Okay. Now, in reality, all the s orbitals are spherically symmetric. That is, the probability of finding an electron at a given distance is equal in all directions. So it is symmetric, spherically symmetric. So in any direction, you can find an electron. Okay. So it is also observed that the size of the s orbital increases with the increase in n. So as your n increases, the size of s orbital also increases. So 4s is the biggest one, then 3s, 2s and 1s. So as you increase the principal quantum number, the size of the s orbital also increases. Boundary surface diagram for three 2p orbitals, okay, is shown here. So now these are for p orbitals. Those are for s orbitals, what I showed you. So these are for s orbitals. These are for s orbitals. These diagrams are for p orbitals. In these diagrams, the nucleus is at the origin. Okay. Here, unlike s orbitals, the boundary surface diagrams are not spherical. Okay. Now, for s orbitals, they are spherical in shape, but for p orbitals, they are not spherical in shape. Instead, each p orbital consists of two sections called lobes. So, they are in the form of lobes, two lobes attached to each other. Okay, that are on either side of the plane that passes through the nucleus. So here at the center is the nucleus. All that in the center is the nucleus, and both the lobes pass through the nucleus. Okay. Both are present on the either side of the plane. And this is X, Y and Z plane. So both are present on the either side of the plane passing through the nucleus. Now the probability density function is 0 on the plane where the two lobes touch each other. So it is 0 here where both the lobes touching each other. This area is 0. The function probability density function is 0. Okay. The size, shape and energy of these three orbitals are identical. Okay. Now they differ, however, in the way the lobes are oriented. So their size, shape and energy is same for all three. But only thing the orientation is different. One is in XY, other one is in Z. So one is in X. So this is on X orbit, this is on Y orbit and this is on Z orbit, right? So their orientation is the one which is changing. So this is 2px, 2py and 2pz, because this is on x-axis, this is on y-axis and this is on z-axis. Only their orientation is the one which is changing. So since the lobes may be considered to lie along the x, y and z-axis, they are given the designation as 2px, 2py and 2pz. Why? Because this is p orbitals. P orbital starts from the 2 subshell. So 2px because it is on the x-axis, 2py because it is on the y-axis, and 2pz because it is on the z-axis. So it should be understood, however, that there is no simple relation between the values, okay, and the x, y, and z direction. So there is no simple relation. For other purpose, it is sufficient to remember that because there are three possible values of magnetic quantum number, there are therefore three p orbitals whose axes are mutually perpendicular. Okay, there are three possible values for magnetic quantum number of p orbitals. Therefore, there are three p orbitals and they are present on three axes which are mutually perpendicular to each other. Okay, like s orbitals, p orbitals increases in size and energy with increase in the principal quantum number. So like s orbitals, as you increase the principal quantum number, the size of the p orbitals also increases. Okay. No. Further, like s orbitals, the probability density function for p orbitals also pass through the value 0. Just like s orbitals, there is a probability function for p orbital, then probability density function for p orbital is also passes through a range of 0. Besides, at 0 and infinite distance, as the distance from the nucleus increases. So as the distance from the nucleus keep on increasing, there is a point where you attain a 0 or an infinite distance. Now the number of nodes are given by the n minus 2. So for s orbitals, the number of nodes can be found by n minus 1. For p orbitals, it is n minus 2. So the number of radial nodes. Now here you have radial nodes because they are present on the axis. So the radial nodes for 2 it is 0. Now for 1, for 3p it is 1, for 4p it is 2 and so on. Now for L is equal to 2, the orbitals is known as d orbital and the minimum value of principal quantum number n has to be 3 as the value. Now the d orbitals, it starts from the principal quantum number 3. So as the value of L cannot be greater than n minus 1, there are 5. Okay, this is because the value of L cannot be greater than n minus 1. Now there are 5 magnetic quantum numbers for d orbitals. These are minus 2, minus 1, 0, plus 1 and plus 2. So for L equals 2 and thus there are 5 d orbitals. So there are how many d orbitals? There are 5 d orbitals. Now the 5d orbitals. Okay. The orbitals are designated as dxy, dyz, dxz, dx square y square and dz square. Now I'll show you. Now this is dxy because it lies for dx and y. Now this is y, this is x. Now this is lying in between x and y. So that is why it is dxy. Now this is dxz. Both four lobes, they present on the in between of z and x. Okay, so that's why it is dxz. Now here the lobes are present on in between x and y. Sorry, in between z and y. So it is yz. Okay, so they are present in between z and y. This is x square y square because they are present exactly on the axis. So this is present on x and y axis. So that's why it is dx square y square. And this is present on the only on the z axis and the other one is around it. So this is dz square. So these are the shapes of the d orbitals and their designations. So the shape of the first four d orbitals are similar to each other, whereas that of the fifth one is dz square. Now all the four, that is dxy, dyz, dxz and dx square y square, they have similar shapes. Only thing is that the first three, that is xy, yz and xz, they are present in between the axis, and x square, y square, they are present on the axis. Now, only difference is with the dz square. But all the 3D orbitals are equivalent in energy, even though there is difference in the shape of dz square, but their energy is same for every orbit. Okay, now every 3D orbitals have same energy level. The 3D orbitals for which n is greater than 3 also have shape similar to 3D orbitals. Now maybe 4D, 5D, any d orbitals, they have same shape, similar shape, but only thing is that they differ in energy and size. So besides the radial nodes, that is probability density function is 0. The probability density function of NP and ND orbitals are 0 at the plane S passing through the nucleus of the origin. Okay, so here it is 0. Okay, at this particular points, the center points of all these, it is 0. Okay. In case of pz orbitals, xy plane is a nodal plane, right? pz, the lobes are present on z, where x and y are just passing through it. So that is the nodal plane. Now, in case of dxy orbital, there are two nodal planes passing through the origin by bisecting xy plane containing z axis, right? So there are two planes. This is one which is bisecting the xy plane. So there are two planes. Now these are called angular nodes. Now these are called angular nodes because they are present at an angle, and number of angular nodes are given by L. Now one angular node for p orbital, two angular nodes for d orbitals. Okay, one for p orbitals and two for d orbitals, and so on. So the total number of nodes are given by n minus 1. Total number of nodes is given by n minus 1. That is sum of L, that is your angular nodes, and n minus L minus 1 is your radial nodes. Okay. Now, energy of the orbitals. Now, what is the energy of the orbitals? Now, the energy of the orbitals, energy of an electron in an hydrogen atom is determined solely by the principal quantum number. The energy, as I told you, principal quantum number, it deals with the energy and the size of the orbits, right? Now, so the energy of an electron in an hydrogen atom. In a hydrogen atom, okay, hydrogen atom and hydrogen-like species, that is He plus, Li plus 2 plus. So those are hydrogen-like species. For them and hydrogen atom, it is solely determined by the principal quantum number because they have only one electron in them. Okay, whereas as the energy of the orbitals increases as follows. So their energy level increases. So 1s is smaller than 2s. 2s equals 2p. Their energy level is equal. Now, then 2p is smaller than 3s. Now 3s is bigger. 3s, 3p, 3d, they are equal. Then is the 4s, which is greater than 3d. So, and so on and so forth. So, n is depicted here in this diagram. You can see the energy level. So, this is for 1s. Then you have 2s, 2p. They are on same energy level. Then you have 3s, 3p, 3d. They are on again on same energy level. Okay. Now, although the shapes of 2s and 2p orbitals are different, an electron has same energy when it is in the 2s orbitals as when it is present in 2p orbitals. So the shape, although the shape of 2s and 2p is different, because 2s is a circle, it's a spherical one, right? And 2p is a lobe one. Even though their shapes are different, but the electron has the same energy when it's present in the 2s orbital as when it is present in the 2p orbitals. The energy is same for electrons when they are present in 2s and 2p orbitals. The orbitals having the same energy are called degenerates. So when they have same energy, they are called degenerates. So 2s, 2p are degenerates of 2. 3s, 3p, 3d degenerates of 3. Okay. Now, the 1s orbital in a hydrogen atom, as said earlier, corresponds to the most stable condition and it is called ground state. Okay. Now 1s for hydrogen atom. Okay. It is earlier said that it corresponds to most stable condition, right? Now for that matter, this part is known as ground state. Okay. An electron residing in this orbital is most strongly held by the nucleus. So when an electron is present in 1s orbital, it is more strongly held by the nucleus because it is the closest one to the nucleus. Okay. Now, an electron in 2s, 2p or higher orbitals in an hydrogen atom is in excited state. So when in hydrogen atom, the electrons from 1s orbitals by absorbing energy, when they move to 2s, 2p or for that matter any higher levels, those electrons are known as excite, or those electrons when they come to, now from 1s, if an electron from hydrogen comes to 2s, that is known as excited state. Okay, it excited from 1s to 2s. Now the energy of an electron in a multi-electron atom, unlike that of the hydrogen atom, depends not only on its principal quantum number, that is shell, but also on its azimuthal quantum number, that is subshells. Now, for hydrogen, it only depends on principal quantum number. But for the electrons which have multi-electrons, that is for an atom which is multi-electron, they have various electrons more than one. For those atoms, the energy level, it depends not only on principal quantum number, but it also depends on the azimuthal quantum number, that is your subshells. So that is for a given principal quantum number, that is S, P, D, F, all the different energies. And the main reason for having different energies of the subshells is the mutual repulsion among the electrons in the multi-electrons atom. Now, why do you have various, why, like hydrogen, why don't they have a similar thing? Or why there is a difference is, the main reason is because as the number of electrons are more, what happens? They are like charges, right? Both the electrons are negative charges. So these will start repulsing. They will start opposing each other because as I told you, there is a basic law that is like charges repel each other, unlike charges attract each other, right? So as the number of electron increases, there is repulsion. So these electrons, they start to push each other. That is why the energy levels differ for the multi-electron atoms. The only electrical interaction present in hydrogen atom is the attraction between the negatively charged electron and the positively charged nucleus. So for hydrogen, it is only between the electron and the proton because it contains only one electron and one proton. But for other matters, other atoms which are higher than hydrogen, they have two or more electrons in them where this electron will start repulsing each other, where they will start pushing each other. Okay, so for multi-electron atoms, besides the presence of attraction between electron and nucleus, there are repulsion terms between every electrons and other electrons present in the atom. Even though those multi-electron atoms, they have a attraction between the nucleus and the electrons, still this will repel the other electrons present in them. Now, thus the stability of an electron in multi-electron atom is because total attractive interaction and more than the repulsive interaction. Now, the stability of that, now you can see that there is attraction between electrons and protons, but there is also repulsion. So there might be chances of unstable condition, but the stability of the atom is maintained because the attraction of electrons and nucleus is more than the repulsion between the electrons. Okay, so there is the total interaction are more than the repulsion interaction. Okay, so in general, the repulsive interaction of an electron in the outer shell with the electrons in the inner shell are more important. Okay, on the other hand, or the attractive interaction of electron increases with increase of the positive charge, that is Ze in the nucleus. Now, presence of electrons in the inner shells. The electron in the outer shells will not experience full positive charge of the nucleus, right? Because this is the nucleus, this is one orbit, other orbit. Here there are electrons, here also there are electrons. If I add one more orbit, on that orbit also there will be electrons present. Okay, but the attraction that these electrons feel will be more than the electron which is present on the outer shell, right? They will feel less. So the effect will be lower due to the partial screening of positive charge on the nucleus by the inner shell electrons. The reason is the effect, the attractive effect on this electron is lowered because there is a shielding. Shielding means what? These electrons are covering the nucleus. Okay, so it is because of the partially screening effect. So this electrons, they are screening the nucleus. They are hiding the nucleus from this electron. So the effect of attraction, positively charged attraction for this electron is lowered. This is known as shielding of the outer shell electrons from the nucleus by the inner shell electrons. So this is known as shielding. Shielding means what? They are hiding the nucleus from the outer shell electrons. So shielding of outer shell electrons from the nucleus by the inner shell electrons. Okay, and the net positive charge experienced by the outer electrons is known as effective nuclear charge. So whatever positive charge experienced by this outer electron is known as effective nuclear charge. Now, even though there is a shielding effect, that shielding effect can increase, or the outer electron can experience this attraction with the increase in the nuclear charge. So as you increase the charge on the nucleus, this electron can also feel the attraction. Okay. In other words, you can say that the energy of interaction between the nucleus and electrons, okay, it decreases with increase in the atomic number. Okay. So as the atomic number increases, the shells will also increase, right? So as the shells increases, the electrons will move further and further away from the nucleus. So it will decrease with the increase in the atomic number. Now, both the attractive and repulsive interaction depends upon the shell and shape of the orbitals in which the electrons is present. For example, now, both the attractive and repulsive interaction, they depend upon the shell and shape of the orbitals where electrons are present. Electrons are present in spherical shaped s orbitals, shields the outer electrons from the nucleus more effectively as compared to electrons present in p orbitals. Now, the electrons that are present on the s orbitals shield the outer electrons from the nucleus more effectively as compared to electrons present in p orbitals, Why? S orbital is like this, so they can shield more effectively, and p orbitals are like this, so the electrons present here can't be shielded, right? Similarly, electrons present in p orbitals shield the outer electrons from the nucleus more than the electrons present in d orbitals. Now, s orbital can shield more than p orbitals, but p orbitals can shield more than the d orbitals. Okay, even though all these orbitals are present in the same shell. Okay, further within a shell, due to a spherical shape of s orbital, the s orbital electron spends more time close to the nucleus in comparison to p orbitals electron, which spends more time in the vicinity of nucleus in comparison to d orbitals electron. Now for s orbitals, the electrons, they spend more time close to the nucleus, because here is p or s orbital which is spherical, then you have p orbital which is like this, then you have d orbitals which is like a flower. So the electrons present in s orbital spends more time close to the nucleus. For p orbitals, they are present in the vicinity. Vicinity means they are present neither close nor far, in the vicinity. For d orbitals, which is further away. So in other words, for a given shell, that is principal quantum number, the Z effective, okay, the effective nuclear charge experienced by electron decreases with the increase in azimuthal quantum number, that is your subshells. This is a shell, principal quantum number, that is 2. Then you have 2s, 2p, and okay, I'll take 3. Now you have 3s, 3p, 3d. These are subshells, right? 3s, 3p, 3d. This is your principal quantum number, that is 3. Now, the electrons present in these subshells, so their effective nuclear charge decreases as the azimuthal quantum number increases. So as the subshells increases, so S will have more nuclear charge, P will have less, D will have less. So this is decreasing as you go from S, P and D. That is, the s orbital's electron will be more tightly bound to the nucleus than p orbital electron, which is in turn will be better tightly bound than the d orbital electrons. Okay, so s will be tightly held, then p will be better tightly held than the d orbital, which is too loosely held. Okay, the energy of electron in s orbitals will be lower, that is more negative than the p orbital electrons, which will have less energy than the d orbital electron, and so on. So their energy will be decreasing as they increase. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to the splitting of energy levels within the same shells. Now the shielding of nucleus is different for electrons, right? Closed one will be more tightly held. So as you go further and further, the shielding will decrease. Now this shielding will increase. Now this difference leads to the splitting of energy levels within the same shell or same principal quantum number. That is, energy of electrons in an orbital, as mentioned earlier, depends upon the value of n and l. Okay, n is your principal quantum number, l is your azimuthal quantum number. So it depends, the energy of electron in an orbital is dependent upon your principal quantum number and azimuthal quantum number. Now, mathematically, the dependence of energy of the orbitals on n and l are quite complicated, but one simple rule is that mathematically it is very complicated, but there is one simple. The lower the value of n plus n for an orbital, the lower is its energy. Okay. Now, lower value of n plus l, n plus l is your principal quantum number and azimuthal quantum number. So the lower the value of n plus l for an orbital, lower is its energy. If two orbitals have same value of n plus l, the orbital with lower value of n will have the lower energy. This is the rule where the lower the value, the less the value of n plus l. If you calculate n plus l, the lower the value, the orbital's energy is less. If two orbitals have same value of n plus l, okay, the orbital with lower value of n will have the lower energy. Okay. So here it is given. Now this is the energy level. 1s, 2s, 2p is slightly higher than 2s. Then is your 3s, 3p, 4s, and 3d is slightly higher than 4s. Okay, so these are the different energy levels. It may be noted that different subshells of a particular shell have different energies in case of multi-electron atoms. Okay, so they have different energies in case of, so a particular shell will have different energies in case of multi-electron atoms. However, hydrogen, these have the same energy. Lastly, it may be mentioned here that energies of the orbitals in the same subshell decreases with increase in the atomic number. Okay, energies energies of the orbitals in the same subshell decreases with increase in the atomic number. Okay. For example, energy of 2s orbital of hydrogen atom is greater than the 2s orbital of lithium, and that of lithium is greater than that of sodium, and so on. So the 2s orbital of hydrogen atom is greater than the 2s orbital of lithium. That of lithium is greater than that of the sodium. So this will go on. So there can be changes with the size. So today we have seen about the shape of the orbitals, different orbitals, that is s, p, and d. Okay, shape of atomic orbitals and how they are arranged. What is their effect on the electrons and nucleus. So in our next video, we'll see about the filling of these orbitals and some principles regarding that. Okay. So thank you for watching my video. Please do like, share and subscribe to our channel.